Okay, so our project that we did was predicting fuel economy of older cars. It was by me, Evan, Kaylee, Bingu, and Michael. So our data set is called Auto MPG. It came from StatLib from library at Carnegie Mellon University. It was collected and used in 1983. It contained 8 predictor variables and 1 response variable, which we'll talk about in just a little bit. The data was collected from the 1970s to the 1980s, and it was previously used in a 1983 Statistical Association Expo, as well as published in a paper by Ross Quinlan in 1993. So some previous research that has been done, it was done by Ross Quinlan, and then a more accurate one that matched up with our data set was published on medium.com, and it was used to study if they could predict miles per gallon from the variables. They covered machine learning methods, which they did gradient boost decision tree regression, decision trees, k-neighboring regression, and random forest. So they used all of the methods mentioned above, and then they selected their best one, which was GXBoost. They primarily focus on predicting miles per gallon, emphasizing the origin. So our research questions are: which factors are most important in predicting miles per gallon? What is the 95% confidence interval for prediction of a single miles per gallon for a given car? And if our data contains any violations, what transformations can we do to possibly eliminate those? So a more in-depth look at our dataset characteristics. The 8 predictor variables are cylinders, displacement, horsepower, weight, acceleration, model year, origin, and brand. And our one single response variable is miles per gallon. So there you can see how each data point is measured. So our data had originally 398 observations, but 6 of them were removed for missing values in horsepower. So we had 392 observations total. We initially wanted to analyze brand as a predictor. However, we found that the predictive power was very similar to origin, so we decided to remove it for a more simpler model. And then we ultimately ended up splitting origin into 2 variables, O1 and O2. O1 is equal to 1 if it was an American produced car, and then 0 otherwise. And O2 is 1 if it's European, and 0 otherwise. So now Evan will talk about our preliminary analysis.
So for our preliminary analysis, we're going to be looking at the scatter plots of each of the predictor variables and the response variable miles per gallon. So on this first slide, we can see the effect that cylinders, displacement, and horsepower have on miles per gallon. In the last 2, we can see that there is an inverse and nonlinear relationship between the predictor and the response. And in the first one, we can see that there's also a downward trend between cylinders and miles per gallon. So next we have the scatter plot of miles per gallon and weight. So we can see here that it's also a negative relationship and nonlinear. So that means that the scatter plots of miles per gallon versus displacement, horsepower, and weight all appear to be nonlinear. So we'll need to be transforming that later on. For the scatter plot of miles per gallon and acceleration, we can see that the relationship is linear, but it has a weak positive relationship. Additionally, one problem we see here is that the variance in the residuals is non-constant, so we'll be needing to transform the data further to correct that. So here we can see the scatter plot of model year and miles per gallon, and also origin versus miles per gallon. So in both of these cases, we have a positive linear relationship between the different factors. The model year we treated as a continuous variable because there are so many different years that the cars were built in during the time period which this data set was collected. And the origin, because there are only 3 different factors, that's why we decided to use the 2 indicator variables to be able to see the effect that origin has on miles per gallon. So the scatter plots for miles per gallon versus model year and origin versus model year both have a positive linear relationship. The origin year shows us that as the years increase, the vehicle gets better fuel economy. And from the origin, we can see that cars produced in Japan have better miles per gallon than those produced in Europe and America. So an overview of our preliminary analysis, based on the scatter plots, it appears that the predictor variables of cylinder, displacement, horsepower, and acceleration increase when miles per gallon decrease, indicating an inverse relationship. And as model year increases, miles per gallon also increases. So from the original data set, we noticed that brand and origin were closely related and were giving us similar results. So to remedy this problem, we created dummy variables for origin, which are O1 and O2 as previously described, and we decided to omit the brand data completely.
Wait, we didn't ever fix that slide.
Oh gosh, guys. Okay.
Sorry, I noticed.
Let me know when.
As soon as I hide this thing. Okay, go. Wait.
Okay, so here we can see that the scatter plots for miles per gallon versus model year and origin versus miles per gallon both have a positive relationship. The origin year shows that as time increases, the miles per gallon gets more efficient. And we can also see in the origin plot that the cars produced in Japan have better miles per gallon than vehicles produced in both Europe and America. So for an overview of our preliminary analysis, we can see that from the scatter plots, cylinders, displacement, horsepower, and weight increase when miles per gallon decreases, and acceleration and model year increase when miles per gallon increase. So from the original data set, we noticed that brand and origin were closely related in giving us similar results. So in order to remedy this problem, we created dummy variables O1 and O2 as previously described for origin, and we decided to completely omit the brand data. We also discovered some potential problems in our preliminary analysis. The main one of these is the problem of nonlinearity. So this is most apparent in the miles per gallon versus displacement, horsepower, and weight. Additionally, it appears that miles per gallon versus displacement, horsepower, and weight are all similar, and this may lead to problems with multicollinearity, which we will analyze later. There is also a problem with non-constant residual variance between miles per gallon and acceleration, so we're going to need to perform some transformations with this. But overall, all of these problems we believe can be remedied with transformations. So here is an overview of all of the relationships between the response variable miles per gallon and all of the predictor variables. So we can see the inverse relationships in some of the variables and the nonlinear relationships. But what this also shows is the problem with multicollinearity between some of the predictor variables. So ideally, there would be no relationship indicated by a low correlation. However, in this correlation matrix, we do see that some of the relationships between the predictor variables are pretty high. So that's going to need to be fixed later on.
So now that we've addressed our preliminary analysis, we can start building our model. To make the data more workable, we created two dummy variables, O1 and O2, as discussed. To start building our model, we performed an ANOVA test to see which variables would be significant in the original form of the data. The output from the ANOVA indicated that cylinders, displacement, horsepower, weight, model year, and O1, indicating American origin, were all significant in predicting miles per gallon. This can be seen once again in the output from the ANOVA function. To test for normality and constant variance, we used the Shapiro-Wilk and Brown-Forsyth tests, respectively. Running the Shapiro-Wilk test, we found a very small p-value, indicating that the residuals errors were not normally distributed. Running the Brown-Forsyth test, we found a large p-value, indicating that the residuals do have a constant variance. These results can be seen once again in the output from the two tests. To normalize the data, we decided to take the natural log of MPG. In addition, we took 1 over displacement, 1 over weight, and 1 over horsepower to correct the nonlinear relationship between these variables and MPG. The results of one of these transformations can be seen below, in MPG versus weight before the transformation having a nonlinear curved negative relationship, and after the transformation having a much more linear positive relationship. The results of all transformations can be seen in this matrix of scatter plots, as we can see a lot of the nonlinear relationships have been corrected, as well as some of the variance issues we were having before we transformed the data. Following our transformations, we once again performed the Shapiro-Wilk normality test and Brown-Forsythe test, which both confirmed that our transformations had corrected the problems we found in linearity assumptions for the model.
So next, we conducted a subset analysis. We plugged all our information into R, and this is what came out. Originally, we looked at model 7 here because it had the best SEP, R squared, adjusted R squared, CP, AICP, SBCP, and PRESS-P values. But we also looked at our initial ANOVA and said, well, number 6 is extremely similar to it, so let's move along with that one. So next we performed a k-fold cross-validation, looking at first a model with everything except the second origin dummy variable, and then a secondary model that also removed acceleration. The first model has a very good RMSE value, and so does our second model. We, however, did decide to go with the model without acceleration because it was more true to our original ANOVA check at the beginning. Both of these models also passed the Brown-Forsythe and the Shapiro-Wilk tests. So next we have to look at our outliers and influential points. When we use influence plot in R, we found that these 5 points were our outliers and or influential points. The first 3 points listed here actually fall under cars with 3-cylinder engines, which in our data we only have 4 of. So we decided that those were influential because there were so few of them, so we kept them. The next one is 261, which actually passed all of those tests, and so we decided to keep it. The last one we did get rid of because it seemed like a normal data point that was just an outlier. So we got rid of it and adjusted our data. So next we wanted to look at multicollinearity. We looked at these 5 combinations, and the biggest one was weight with displacement and horsepower. We decided to, at the end of the day, to keep this because 1, it's only a little bit over the 10 mark, and 2, in a car, a lot of these things are kind of related in general, and we felt that it would be unfair to keep one of them out. Basically, it would weight some variables one way and some variables another. This is the added variable plots, and you can see that all of these variables that we've chosen do contribute something when the others are there. So finally, with our last model, we decided to do a Shapiro-Wilk and a Brown-Forsythe test, both of which passed with flying colors. So here's our final model. You can see the transformations we've done total, and then we can see our output from R and see what kind of things we're looking at.
Okay, thanks, Mike. After we got the final model, we are able to answering our research questions. The first one is which factors are most important in predicting the miles per gallon. We got number of cylinders, displacement, horsepower, weight, model year, and the origin of the car. Next, question 2 is about the prediction power of our model. We want to get a 95% confidence interval for a given car existed in the study, but was not used to create our model. So here you can see the Cobra car. We used its parameters, and we got a confidence interval between 19.313 to 30.541 with a fitted value of 24.2868. And the actual value of its MPG was 23.6. We can see they are in the confidence interval and quite near with the fitted value. So next is our question 3. The question 3 we asked is whether our data has any violations. If we have, can we just transform to fix them? So the answer is yes. So our original data has some linear relationships between some predictors with MPG, and there is also multi-collinearity between some variables. And the residue error is not normally distributed, but I will mention it in the next slides. We do the transformation on the MPG, is to take the natural log, and then we take the reciprocal of 3 predictors like displacement, horsepower, and weight. And then we remove the acceleration from the predictors. And another thing we did is we create the dummy variables for the orange. So after we did all these transformation and model selection, we do fix our problems for the multi-collinearity, non-constant variance, and non-normality in our data set. So after answering our question, we want to compare our model with the reference paper. Actually, we got the data from the reference paper, but they did not do modeling on this data. And then we found another paper that used this data. As Katie mentioned before, they apply 4 different machine learning methods. And then what they got is they built a model that could reliably predict the car's MPG given some information within 2.5 MPG of the actual value. And our model that could predict the car's MPG within 5.5 of the actual value. And also we can got a 0.9 range for a mean response prediction. So Evan will summarize the pros and cons next.
Yeah, so here we're going to discuss some of the pros and cons between our linear regression model and the GXBoost model that was used. So for our linear regression, one of the pros are that it's easily adjusted for new models. So if you wanted to take away or add some of the predictive variables, it would be easy to do so. And it's also a more easy to interpret approach. Some of the cons of our approach is that it's less accurate compared to GXBoost, and it's also more susceptible to human bias and error because we did make some subjective decisions throughout. For the GXBoost, it was more accurate. It included training and testing, and it uses a more modern machine learning approach that is more adaptable to cars, including newer cars. However, the GXBoost is heavily dependent on the origin predictor, and it's also complicated and very dependent on advanced computing power. So in conclusion, from this data set, we learned that an accurate estimation of miles per gallon in older vehicles can be predicted from number of cylinders, horsepower, displacement, weight, model year, and dummy variable that we use to indicate the origin of the vehicle. We also think that our model is more appropriate than the one that contains all of the original variables. But the largest limitation to our model is that there are factors in fuel efficiency or miles per gallon that we do not have access to in the data set, such as drag, weather, driver mood, and also the size of our data set limited us a little bit.